Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hello everyone. Today I'm glad to share our research experience on the OBD-II Bluetooth device. My name is Aaron and my partner is Spencer. We are from VicOne, which is a subsidiary of Trendmicro and established in June last year. At VicOne, our primary focus is automotive security. And our topics for today is remotely hacking a car through an OBD-II Bluetooth dongle. Before we begin this topic, I would like to introduce some common attack vectors in automotive. From this diagram, we can see that the car is composed of various components such as tire pressure monitoring system, keyless entry, anti-theft engine control unit. Among these numerous modules, in-vehicle infotainment system and telematics relay elements such as mobile apps, Wi-Fi, Bluetooth, etc. are preferred entry for hackers to remotely access the vehicle. And OBD-II we will introduce later. In-vehicle network has often been a prime target for hackers in the past because it includes several modules that allow remote access, such as Bluetooth, Wi-Fi, cellular network, and web browsers. It is also commonly connected to the CAN bus network for data exchange within in-vehicle network. So, if a device is remote accessible and it access to the CAN bus network, it could be the perfect target for hackers because hackers could remotely access this device and then control the CAN bus network to impact the car. This is the pin layout for OBD-II. OBD-II is primarily used for vehicle diagnostics, and both the repair shops and original equipment manufacturers may use the OBD-II to update the car's ECU firmware or some other firmwares. As shown in the diagram, there are the pins that provide access to the CAN bus network. Additionally, OBD-II provides a 12 voltage output, which means that devices connected to it do not require an additional battery and can be powered directly through OBD-II. In addition to being used by car manufacturers for diagnostics, OBD-II has also seen the emergence of numerous products that provide users with mobile app functionalities. These products typically come in the form of dongle that can be connected to the OBD-II port and allow remote diagnosis of various car conditions using Bluetooth connectivity. Furthermore, there are dongles provided by telecommunication companies, such as this one is from Verizon. The purpose of this dongle is to provide a cellular network connection within the vehicle and convert it into the Wi-Fi hotspot for smartphone or other device inside the car to access the internet. Additionally, this dongle offers convenient services such as roadside assistance and automatic reporting of accident locations. T-Mobile also offers a similar multifunctional dongle. They provide users with a cellular network hotspot and include a GPS module. This dongle continuously collect and record information such as vehicle locations. So, after install wireless OBD-II dongle, now your car is connected. It's exposed to hackers. Next, we will provide an example to illustrate how to hack an OBD-II dongle. Here are the specifications of our target OBD-II dongle. The OBD-II dongle is pre-installed on specific model of the brand's vehicle in Taiwan. It provides iOS and Android apps for users to view various parameters through their smartphones. The smartphone and OBD-II dongle connect via Bluetooth Low Energy. Additionally, firmware updates can be performed on the dongle from mobile device using Bluetooth. This is a simplified architecture of the dongle. On the left side, we have the mobile app, which can display various car information such as engine RPM, temperature, and more. This piece of information are obtained by the dongle through the CAN bus. Once the dongle acquires this data, it synchronizes and sends it to the smartphone for display. First, let's take a look at how to hack the Android app. The app has several protection mechanisms that need to be bypassed, including online registration, vehicle identification number checks, and Bluetooth pairing. Additionally, we need to be able to update malicious firmware onto the dongle. Finally, we need to add the custom Bluetooth command packets to the app to communication with the dongle containing the malicious firmware. Next, let's explain how we bypass the registration verification. The app requires the registration verification before pairing the dongle. During the registration, a network packet is sent for the verification, and if the license plate number and the VIN are not present in the server's database, registration will be failed. The response data will indicate the car data is not in the database. However, we can bypass this verification by just using the APK tool to decompile and patch the APK file. The specific steps involve modifying the sign-up activity.smart file in the APK. In the handle response functions, we change the result from N to Y and send the error code to E003 to bypass the registration check successfully. After pairing the dongle, the app performs another check to verify if the VIN of the vehicle matches the owner of the dongle. However, this check is performed on app side and not within the dongle itself. Therefore, it is possible to bypass this check by just modifying the app. By doing so, one can pair the dongle with any vehicle regardless of VIN ownership. The specific modification is modify the home launcher screen activity.smart file in the app. On the onReceive function, the conditional statement if equals can be removed, cause the app to unconditionally consider the VIN as correct. Next, let's discuss the weakness related to the Bluetooth. By capturing Bluetooth low energy packets, it can be observed that the device does not perform out-of-band authentication and lack man-in-the-middle protection. So this weakness can be leveraged by hackers to gain unauthorized access or perform various attacks. Building upon the weakness mentioned earlier, it is possible to use tools like OBD-II to intercept and crack the long-term key (LTK) and the identity resolving key (IRK). By doing so, an attacker could potentially decrypt all the traffic between the dongle and the connected device, compromising the security and the privacy of the communication. Finally, we can modify the Smiley core of Android app to bypass all restriction and force pairing with the XX dongle device. We don't want to directly disclose the name of the manufacturer, so we will use the XX instead. I modify the firmware file name and repacking the APK. You can update the customized firmware onto the dongle. The firmware file is located in the assets folder of the unpacked APK. The file name includes the firmware version number. After increase the version number, just like if the version is 1.00 and you can increase to 1.0.1, and then you can remotely update the firmware by press the update button within the app. After updating a customized firmware, unfortunately the dongle is broken and becomes the brick. So we attempt a hardware analysis in hope of discovering more information and restoring the dongle. I will now pass it on to my partner Spencer to explain the next part.
Okay, Aaron has talked about how do we modify the Android app and use it to bypass the protection of registration check, VIN number check, and the pairing of Bluetooth. So now we can use the modify app to pair with an arbitrary dongle and use the app to update the firmware of the dongle. So in order to test our idea, we decided to modify the firmware slightly and use the app to update the firmware of the dongle. However, we break the dongle. In order to figure out what is wrong, we go back to check the firmware inside the app, and we figure out the app can only update a part of the firmware. As you can see in this diagram, the app can only update firmware from the address 0x8000 to 0x1F000. So it is very likely that the code in the first part of the firmware has some kind of integrity check. So if the updated firmware does not pass the integrity check, the dongle cannot boot anymore. Therefore, to let the dongle accept our modified firmware, we need to have the algorithm for the integrity check. But if we want to figure out the algorithm for the integrity check, we need the first part of the firmware. So the question is there a way to have the firmware of the first part? To answer this question, we go back to the hardware itself, and we decided to take it apart. And our idea is if we can download the first part of firmware from the hardware itself, then we may be able to figure out the algorithm for the integrity check. And if we have the algorithm for the integrity check, then we can make the dongle to accept our modified firmware. As shown in the picture, the microcontroller used by this dongle is an XP S9KEAZ128A. And we downloaded the datasheet of this microcontroller and try to figure out if there is a way to let us down the firmware from the hardware itself. We quickly figure out this microcontroller has a UR port for serial communication and another port of SWD debug port. So it may be possible that we can download the firmware from the debug port. As shown in this picture, this is our setup for firmware dumping. The dongle itself is powered through the OBD port, and it is connected to Arduino device. The reason we use the Arduino device is we want to sniff the traffic in the CAN box. And you can also see there are some very thin wire. This thin wire is connected to the SW debug port and the UR port. And as discussed in the previous slide, it is possible that we may be able to dump the firmware from the SWD debug port. We connected the debug port to a J-Link device and try to use a J-Link device to dump the firmware. Unfortunately, we encountered another problem. As shown in this screenshot, you can see the J-Link tells us it cannot dump the firmware because the readout protection is set. In order to dump the flash memory, we need to unsecure it first. However, unsecuring it will trigger the mass erase. So we need to figure out another way to disable this security feature. If we cannot disable it, we cannot have the firmware. We check the datasheet of the microcontroller and figure out this is a hardware security feature. If it is not enabled, we are allowed to dump the firmware through the SWD debug port. However, if it is enabled by setting the bits of flash security register to 0001 or 11, the flash dumping is not allowed. It means we cannot dump the firmware without mass erase it first. However, the developer left a backdoor for us, and we can use this backdoor to disable this hardware security feature. Yes, I know it is ironic. The developer enabled a hardware security feature, but in the same time, they leave a backdoor for us to disable it. We discovered this backdoor through reverse engineering the firmware that is embedded in the Android app. As shown in this snippet of code, there is a hidden function that allows us to overwrite the byte on the address 0x4OE of the flash memory. What is the function of this byte? As shown in the above table of the datasheet, The byte happened to be the flash protection byte. And the flash security register we mentioned earlier is controlled by the two least significant bits of this byte. Therefore, we can use this backdoor to overwrite the flash protection byte. Once the hardware protection is disabled, we can dump the whole firmware of the dongle through the SWT debug port. How to use this backdoor? Remember that besides of wiring to the SWT debug port, we also have wired lines to the UART serial port. As shown in this screenshot, we can use the built-in terminal application of Windows to connect to the hidden console of the UART of the dongle through a USB adapter. At first, the hidden console will not prompt what you type in. We need to use the command mfg to enable the prompting. After that, we can use the wf command to overwrite the flash protection byte. We disabled the hardware protection by setting the flash security register to 10. Now we can dump the whole firmware from the SWT debug port. Now we have the whole firmware of the dongle. We use the reverse engineering tools to analyze it. And as shown in this slide, this is the summary of our findings. The flash memory is divided into several parts. The first part from the address 0x0000 to 0x9000 is used for boot up, and the code for integrity check of the updatable portion of the firmware is also located in this area. 0x9000 to 0x8000 is used to store some configuration data, such as the serial number of the dongle and the VIN number of the vehicle. The portion from 0x8000 to 0x1E000 is updatable and can be updated by the Android app. There is no surprise, most functions of this dongle are implemented in this portion of the flash memory. And the rest memory from address 0x1E000 is used for log and other data. We also find out the flash protection byte will be overwritten and the protection for flash dumping will be re-enabled each time after the reboot. Besides, the hidden debug console is also disabled after reboot. It means if you want to dump the flash memory again, you need to repeat the procedure we mentioned earlier again. But the most important is that now we have the integrity check algorithm now. Therefore, now we can update the firmware without making it a brick anymore. Now we have the whole firmware of the dongle and the integrity check algorithm for the updatable firmware. As shown in this slide, this is the algorithm for the integrity check. You can see it just sums up every 16-bit word of the updatable firmware. You may notice that this algorithm is pretty simple. If time is given, it is no surprise that after some try and error, many hackers can figure out this without the whole firmware. Now let's talk about what can an attacker do. As illustrated here, we have come up two possible attack scenarios. The first one is that an attacker can compromise someone's mobile phone first. After that, the attacker can use the mobile phone to connect to the OBD-II dongle and update the dongle with modified firmware. Once the firmware is updated, the attacker can send out arbitrary CAN bus messages through the OBD port from the dongle. Another scenario is that an attacker can install a modified Android app on his own mobile phone. Remember that, as discussed earlier, we can bypass the protection of BLE pairing and other checks to pair our phone with an arbitrary dongle. Therefore, an attacker can get close to an arbitrary car manufactured by this vendor and use his own phone to connect to the dongle inside the car. After that, the attacker can update the firmware of the dongle and use the dongle to send out arbitrary CAN bus messages, just as we discussed in the first scenarios. Now we can send out arbitrary messages to the CAN bus, but what can we do? To find out what can we do, we surveyed several OBD-II products online. Some of them can be used to monitor the status of a car. Some of them can be used to adjust the engine parameters. However, we wanted to try something more interesting but not too aggressive. Finally, we found a kind of product that's called automatic window closer. This kind of product can be plugged into the OBD-II port, and when it detects the owner uses a remote to lock the car, it can automatically close the windows for the owner. But it can only close windows. If we demonstrate how to remotely close windows of a car, I bet that you will say it's so boring. Our idea is that if it is possible to close the window through the CAN bus of OBD-II, it is possible to open the windows. To figure out this, first we use some devices to sniffer and record the CAN bus messages between the window closer and other ECUs. The recorded messages are shown in the left-hand side of this slide. After analyzing the messages and some testing, we figure out that Windows on the left-hand side is controlled by the ID 74A, and the Windows on the right-hand side is controlled by 74B, and the response messages use ID 7B4 and 7B5. We also find out the fifth byte of the message is used to specify which window is targeted. After some try and error, finally we happen to figure out that if we change the 300 bytes to 3FF, we can open a window instead of close it. Now we can open the windows instead of close windows. Besides of firmware, we also need to modify the Android app. As shown in these screens, we add some menu items and functions for open window and close window. Moreover, we also need to add some commands to the BLE communication to tell the dongle to send out window control messages to the CAN bus. We have created a demo video to demonstrate our phishing attack scenario. Now, as you can see, this guy is the owner of this car. He decided to park his car here. After that, he get out of the car and use his remote to lock the car. Now the bad guy is here. As you can see, the red LED is still blinking. It means the car is still locked. Now the bad guy uses the modified app to connect to the dongle inside the car. After that, he tried to update the firmware of the dongle. Once the firmware of the dongle is updated, the bad guy can use his phone to control the windows. Okay, this is the summary of the vulnerabilities and the weakness we have discovered for this device. The first is the Android app can be easily decompiled. And the second one is no encryption for firmware in the resource of the Android app, so we can extract it from the app easily. And the next one is online registration can be bypassed, and this can be achieved by just modify the Android app. And then the next one is the authentication of the Bluetooth pairing can also be bypassed. And this can also be achieved by modify the Android app. And the next one is the VIN check can also be bypassed. And this is also can be done by just modifying the Android app. And the next one is the integrity check of the firmware only use a checksum, and it is not very strong and can be easily to figure out. And the last one is the hardware protection can be disabled. It is a little ironic, but the developer understand this hardware has a hardware protection, and then they try to use it, but they also created a developer's backdoor in the same time. So yeah, this is, of course, it's not safe. Okay, let's conclude our presentation by discussing what kind of solution we might need to protect this kind of devices. First, we need a secure firmware update mechanism. As we have demonstrated, a simple checksum is not enough. Nowadays, many devices are updatable through OTA. Therefore, how to securely transfer the firmware and how to make sure the integrity of the firmware is an important topic. Second, the developer for no matter software or firmware need to have some sort of knowledge of security. As we can see in this case, the developer knows that there is a hardware protection feature. They do enable it, but they created a backdoor for us to bypass it in the same time. They also know that they need a protection of the integrity of their firmware, but they choose to use a simple checksum to protect it. This tells us in order to develop a secure device, the developers need to understand not only what kind of security features they needed, but also how to implement these features correctly. And the last but not least, we may need some kind of solution to protect the CAN bus. As we can see in this case, we can send arbitrary messages from the OBD-II port to control the windows of a car. But do we really need to control the windows from the outer CAN bus from the OBD-II port? We believe we may need some kind of solution to monitor or even block messages from a CAN bus to another CAN bus. Okay, thank you for joining our presentation. If you have any question, please don't hesitate to contact us. Thank you and bye-bye.